Okay, yes, once again, it is my pleasure to speak today. I will be discussing tensor networks and machine learning, the way how I understand this subject. This is a quite substantial subject, and I don't claim to have a fully objective view. I approach this subject as a physicist, and I will try to convey my understanding to you today. My talk will not be technical. I see the goal of my presentation is to tell you about some general concepts which emerge in physics and transcended into machine learning. And those concepts might be helpful even in areas which are very, very far from physics, for example, in neuroscience. So I hope that my talk will broaden your horizons. And although I'm not planning to convey or teach any practical skills, I hope that some concepts will stay with you and at some point later on might be helpful. Okay, before we start, I want to discuss what is machine learning. Again, this is a very subjective, very special view at machine learning, but when I started reading about machine learning a few years ago, I realized that, and of course I was not the first one, I realized that many problems of machine learning, or maybe even all problems of machine learning, it depends on your taste and your mathematical attitude, many problems of machine learning can be cast in the form of approximating certain probability distribution. Let's say you have a probability distribution rho of x, and x is a variable. It could be a multidimensional variable, could be continuous, real, or complex, or it could be a binary, or it could be a mixture. It could be whatever you want, and you have a probability distribution. And then the task is to approximate this probability distribution. This is essentially what we need to do, for example, if we want to have a generating model. For example, x could be a multidimensional variable living in a Euclidean space of high dimension. I don't know, we have an image n by n pixels. So we have n squared pixels overall, and each pixel, let's say, is black and white, so it is parameterized by a real number. And then x would be a multidimensional variable encoding this pixel. And then a generative model would be producing or sampling images. There could be images of a particular digit or a particular letter or symbol, or even more complicated, could be an image of a human face. So it means that we have certain probability distribution rho of x, and we will be sampling this probability distribution. We'll be drawing x from this space with a probability given by rho of x. So this is a rather standard task, but it's clear that as a prerequisite for this task, we need to be able to store rho of x in the memory of our computer somehow, which means that we need to approximate rho of x somehow. In the machine learning algorithm, under the hood, we must have some framework to approximate rho of x. So this is just one example. You can have more complicated examples. For example, you want to have a generative model with some parameters, then maybe you want to be able to sample not just one particular digit, but all 10 digits. Then x will be your variable specifying the image, and y will be the label. Y will be the label, which in my case of digits would be which will be a variable which takes one of the 10 values from 0 to 9. And then you have a joint probability distribution. Again, the task under the hood is to approximate this probability distribution. The same is true for the discriminative models, or simply speaking, classifiers. Let's say I have a very simple instance of supervised learning. I want to be able to recognize handwritten digits or handwritten letters. So in that case, x, the image is given, but I want to calculate, I want to calculate the conditional probability. With knowing x, I want to calculate y. Well, usually people would write something like this, but it really doesn't matter. It depends on the notations. So you want to calculate something like p x, y. You want to calculate the probability for your label given a particular image. So this is a classification task. And once you're given an image, x, you calculate P of x as a function of y, you see for which value of y your probability is largest, and then you say this is your correct label. Again, classifier under the hood is a problem of approximating a particular probability distribution. And there are many machine learning methods which more or less explicitly try to approximate probability distributions. These are autoencoders, methods like normalizing flows, and so on and so forth. So my point here is simple. Maybe you were ready to agree with me to begin with, but nevertheless, I spent 6 minutes trying to convince you that many, if not all, tasks of machine learning can be reduced to the problem of approximating probability distribution. So let's take this for granted. Now, as a physicist, if you speak about probability distribution, there are two particular areas of physics comes to your mind. One area is statistical mechanics, and we will speak about that shortly. And another very large area is quantum mechanics. And after speaking about statistical mechanics, the main part of my talk will be about quantum mechanics. So if you have a standard physics education and someone tells you, let's talk about probabilities, these are two chapters of physics which immediately comes to your mind. So what is the statistical mechanics or statistical physics? Statistical physics and statistical mechanics. Within this talk, these are just two exactly the same things. Statistical mechanics is the following, mathematically, it's the following story. You have a physical system, it's an abstraction, and this physical system is characterized by the space of states, which means that you have certain set, and you have variable x, which belongs to this set, and then you have a function on that set. So set S, the set of states, could be a discrete set, or it could be a continuous set, or it could be both. It could include continuous and discrete parts. If you want to visualize things and you think about moving particle, just one moving particle, then X would be two continuous variables, the location of the particle and the velocity. But there are also many examples from statistical physics where X is a discrete variable. For example, it could correspond to a coin being lying on the surface, and there are two positions of the coin: head is up and tail is up. And then X would be a binary variable taking two values, 0 or 1. So whatever your X is, this is your space on which you will define the probability distribution in the following way. You first define the function h, which is called the Hamiltonian, and maybe you recall your mechanics class. If you took one, that Hamiltonian, the value h of x is actually the energy of that state. And then in statistical mechanics, we simply say that the probability distribution is given by this formula. This formula is called the Boltzmann distribution or the Gibbs distribution. And within my talk, these are two exactly the same things. In physics, these two things are slightly different, but for my talk, I don't make any distinction. So let me try to give you a few more details to provide some context. In classical physics, a system is always in a particular state. And in principle, you can measure the state. You can do an experiment and know what that state is. But very often in practice, your system is vast, it's huge, and it's also interacting with the environment. And it's interacting with the environment in an uncontrolled fashion. And therefore, it's actually impossible to know what particular state your system is in. And we mask this lack of knowledge, we mask this lack of ability to measure the true state of the system by saying that, well, if you observe the system for a certain duration of time and you continuously, well, you not continuously, but repeatedly try to measure in which state the system is in, you will always get slightly different results. They will be different because the system is interacting with the environment and the state of the system is constantly updating itself. And then we mask this lack of knowledge by saying we will describe the state of the system by a probability distribution. We will not say that the system right now in a particular state, but we say there is a probability of finding the system in a particular state. So there is an axiom, if you wish, or a theorem of statistical mechanics that a system which interacts with the environment always will be described by the probability distribution of this form. It can be derived under certain assumptions. We are not going to do that. That's not important, but it's important that this is one of the fundamental laws of statistical mechanics or thermal mechanics, which was understood largely by Boltzmann a little bit over than 100 years ago. And that's how physical systems behave. And therefore, physicists spent roughly 100 years trying to study this kind of probability distributions. So again, X is some variable. You can think of it as a bunch of binary variables. And H is a function which characterizes the energy of a system in a particular state. Okay. What are the examples? There is a class of simple examples, and simple should be understood with quotes, because these are indeed simpler examples than you can write much more complicated examples. But these examples are not simple enough to be solved explicitly. They are rich enough and they're complicated enough. And these examples are the follows. You say that your physical system consists of n subsystems, particles, or it doesn't matter what it is, and each subsystem has only two possible states, 0 and 1. You can think of your system as consisting of n coins, and each coin could be laying on its head or on its tail, and you have n such coins. In physics, we usually think about particles with spins, and the spin could be positioning itself up or down. Maybe in the context of neuroscience, and I'm a little bit speculating because I'm not an expert, you can say that there are n neurons, and each neuron has two states, on and off, so something like that. This is just a model, and we are talking about mathematics, so there are clearly many applications. And then variable x, which describes the state of your system, will be consistent of it will be a collection of n binary variables. Each variable has only two possibilities. So in the end of the story, the full number of states of the system is 2 to the n. And then also the Hamiltonian, the function which determines energy, and that's the physics part. That's the part which is specific to physics, and it might not be a good model to, let's say, describe brain or to describe something else. We say that h is a quadratic function in terms of variables s. So these models are simple, but they're not solvable. They're not trivial. And if you try to write probability distribution of this form with variable h, which is quadratic in s, you can ask what kind of models, what kind of probability distribution I describe. And if you try to make a connection with machine learning, if we try to go back, physicists study this. Let me go one step back. Physicists study these models for their own sake, and there is huge literature on this, how to solve them numerically and how to solve them analytically. These are not simple models. They're not trivial. There is substantial literature. But you can also ask a very natural question. If you try to combine two of my slides together, you say, hey, there are statistical mechanical models which physicists study for 100 years or at least 50 years. And they describe certain probability distributions using this formula, using Boltzmann distribution formula. Can I bring this to the domain of machine learning and try to see what kind of probability distributions I will describe? You can certainly follow this route, and in the end of the story, what you will discover, you will rediscover what is called Boltzmann machine. Boltzmann machine is an approach in machine learning where people say we will approximate our probability distribution, our data probability distribution, which has no relation to physics, which has no relation to coins or to spins or nothing. This could be images, this could be whatever we want. We will approximate our raw by this formula with h, which is quadratic and binary variables. And this approach is very fruitful. It's called Boltzmann machines. And at some point, I'm not sure exactly how many years ago, 5 or 7 or 10, this was a very fruitful, maybe a little bit more than 10 actually. It was a very fruitful way to build machine learning algorithms, and a good one. So this is one obvious connection between statistical mechanics and machine learning. I do not know if the format admits any questions, but if you do have any questions, I would be happy to take them now. before I go forward with my talk.
No questions here.
No questions. Okay. So I will not speak about statistical mechanics anymore in my talk, but I hope that the logic was clear here. That's why I welcome questions, just in case it wasn't, because the rest of the talk will be similar in structure, but we'll be speaking about quantum mechanics. But before we actually proceed speaking about quantum mechanics, I need to explain what quantum mechanics is. It's much less intuitive in comparison with the statistical mechanics. Statistical mechanics is basically the statement that we have conventional physical system like we see every day. We do not have to think about what you see around you as physical systems, but you certainly can. And usually that creates no problem and no confusion. And then you also take into account that whatever you see around you is interacting with a bigger environment, and that creates probabilities, which are not intrinsic. They are just the result of lack of knowledge and lack of control over your system. And that's how we get statistical mechanics. With quantum mechanics, things are much more nuanced. Because at quantum level, at classical level, let's say, let's say it once again. At classical level, if a system can be only in one of possible states. You have variable x, it belongs to the set S. Let's say the set is discrete, it will be easier. Let's consider the coin, which is laying either on its tail or on its head. So variable x is either 0 or 1, it cannot be both. Now, if for some reason you don't have full amount of knowledge, you're agnostic about parts of your system or how it interacts with the environment, then you can assign probability distributions. You say that x equals 0 has probability p, and x equals 1 has probability 1 minus p, and you have Bernoulli distribution. But this is just, probability is masking lack of your knowledge. In reality, the coin is always in the position up or down, in a position 0 or 1. But quantum mechanically, this is not so. Quantum mechanically, probability emerges intrinsically. And this is, if you hear this for the first time, it will be a complete surprise. And I don't expect to be able to fully explain this, because there is no way to fully explain this. There is only way to make peace with this by maybe thinking about this over and over, but the system could be simultaneously in both states. If we speak about a coin could be in a superposition, what we call a superposition of both states, both with the tail up and the head up. How is that possible? It's very difficult to explain how is that possible, because common language, the language we use every day, doesn't have words to explain how this is possible. This is because the world around us is classical, and we are talking about specifically quantum mechanical effect, which only takes place for objects which are small enough. But of course, I'm sure you heard about the folklore, the cultural reference, or how we would say now, a meme, the Schrödinger's cat. And the famous Schrödinger's cat, it's a classical system, but it could be, but any classical system, if you want to take the concept to the extreme, and every classical system can be considered at quantum level, and therefore a cat can be in the superposition of two states, alive and dead. And that, of course, creates a lot of jokes and a lot of discomfort. Yes? Any questions? No, okay, sorry. That, of course, creates a lot of comfort and a lot of confusion, because we never saw a superposition of two classical states. And in reality, we cannot. There are mathematical theorems, there are clear calculations which show that any macroscopic object like a cat would be in one of the states with an overwhelming probability. A cat would be alive with a probability 0.999, many nines, and will be dead at the same time, only with this probability, or vice versa. So the real cat could be either dead or alive, and the possibility of another state is completely negligible. It's such that we don't have to think about it. But if you, instead of a cat, if you consider a small quantum object, not a real coin, but let's say a quantum spin, and an abstraction of a quantum spin we call a qubit, a quantum system which obeys quantum laws and have only two states, then a quantum spin or a quantum bit, qubit, could be in a superposition of two states with any probability you want. You can have 33% up and 66% down. Well, it should be 67, such that the sum is equal to 1. And that is what people can do. That's what people can experimentally realize. So this is a reality. And also mathematically, there is nothing difficult about it. We just say that instead of, so we say a few things. We say first that now we cannot use probability distributions. Probability distribution rho of x, where x was a variable marking possible states, that was masking our lack of knowledge. This is not good anymore because now the probability is intrinsic. It's not masking any of them. There is no way, there is no conceptual way for you to get rid of this probability. And therefore, probability isn't the right language. And what the right language is, you have variable x, which describe states. It takes, let's say, discrete values and it describes states. And then you say that for each state, you assign a complex number, which is called probability amplitude, psi of x. And psi of x now becomes a function on the space of states. So psi is a function which maps the space of states into complex numbers. Okay, so these are sort of classical states. These are classical states. And function psi is called the wave function. And the jargon is maybe a little bit confusing. The jargon is that psi itself called quantum state. So psi is called quantum state. A second ago, x was a state, but now if I will be saying state, I will actually mean quantum state, and I will mean not x, but the function on the space of x. Okay? So that might be a lot of information to digest, but I will try to go slowly, and I'll repeat that we have the classical space of states S, and it gives rise to what is called Hilbert space. Hilbert space is a mathematical term. It's essentially linear vector space. It's a vector space. Why it's called Hilbert space? Because quite often in quantum mechanics, it's infinite dimensional. But in the context of our discussion, it doesn't have to be infinite dimensional. Therefore, whenever I say Hilbert space, you can simply think of vector space or the same linear space, finite dimensional linear space. That's fine. And the elements of this vector space, of Hilbert space, are complex valued functions, which take variable x, which belongs to variable x, which belongs to the state S, and returns a complex number C. Okay? What happens with the elements of the state, or what happens with the elements of the set S? What happens with the classical states? Classical states now become orthogonal bases in Hilbert space H. What does it mean? For example, consider a qubit. Qubit has two states, head is up and tail is up. So 1 or 0. So it used to be that we have only two possibilities, up or down. Now we have a function which has two values. Psi of 1 is equal A and psi of 0 equal B. We are not worried about normalization now, so we will simply say that A and B are two complex numbers. And then there is a mathematical language which physicists invented, and it's a useful language. And it might be somewhat difficult to make a transition from these notations, which should be completely clear, to these notations. But physicists invented a language saying that instead of writing psi of 1 is equal A and psi of 0 equal B, let us introduce, they said, a basis in the auxiliary Hilbert space. So 1 should be understood as a vector, a basis vector in the auxiliary vector space, and 0 will be another basis vector in the auxiliary vector space. This will be two-dimensional vector space, and then we will parameterize this function by writing this, okay? And then psi now becomes a vector in the vector space. So this vector is called the quantum state, or also it's also called quantum wave function. Okay, so this is basically the quantum mechanics in a nutshell. As you see, it is rather different from classical mechanics or classical statistical mechanics, but now how can I recover conventional physics from quantum mechanics? I should be able to recover conventional probabilities, something I can comprehend intuitively. If I measure the state of my system, what is the state I find my system at? The probability is given by the Born rule, and essentially it's a modulus squared of psi. So this is my main formula. In physics, it's called Born rule, and it says that if you know psi, you can calculate the probability, but psi itself is not a probability. And it's very, very important in physics that psi is a complex valued function, because you can have what is called linear combination of states. Psi are vectors, you can add them to each other. You can add them with complex coefficients, and because of complex coefficients, you can have intricate summation and addition of phases, and after taking the modulus squared, you will have different results. And this is very important for physics. Whether this is important for our talk and whether this is important for machine learning is an open question, which I hope to comment on later on in my talk. But for physics, this is certainly something very, very important. And then if you have psi, you can calculate rho of x eventually using this formula. Now, before we proceed and try to make any connection with machine learning or anything of that sort, let me ask a question. If you have heard something like that before, and maybe your first answer would be, unless you took the quantum mechanics class, your answer would be, well, I never heard of this before, and I couldn't because this is quantum mechanics. It doesn't apply to the world around us as we see it, because the world around us as we see it is intrinsic, it's classical, and therefore we don't know what is going on here. But I actually want to tell you that we discuss the Born rule already in high school, meaning in 8th or 9th, sorry, maybe 9th or 10th grade, if I remember the school program correctly. Whenever we discuss, and I want to make a connection with the high school physics, because at least for some of you, you will be able to see that this is not an exotic thing, and actually this is something completely transparent. In high school, we learn electrostatics. You have electric charges which create electric fields, and each charge create electric potential phi. That's what voltage is all about. Voltage measures the potential, but it also creates the field strength. The field strength is the force which acts on the unit charge if you bring it into the field. And that sounds fancy, but I hope all of us did the experiments with charged particles in school, and if not with charged electric particles, then certainly with charged magnetic objects, and we know that they attract each other or repel from each other, and so on and so forth. So E is an electric field which is created by electric charge, and at the same time, that's the force with which this particular charge acts on other charges. And maybe you recall that there is a superposition principle. If you have a particular configuration of electric field created by one charge, and you have another configuration of electric field created by another charge, if you combine those charges together, if you position them together, to find electric field is very easy. You just sum electric fields produced by each electric charge individually. This is called superposition principle. This is the linearity of electrostatics. This is a linearity at the level of field strength. And I want to stress that this linearity, it's not an approximation. This is a, we don't need to go very, very deep. And of course, any talk like that has certain simplifications, but for this, within the scope of my talk, I want to emphasize this is not an approximation. This is actually something fundamental, because actually electric field can be understood as the wave function of a particle. It's a quantum particle behind the electric field, which is called the photon. And I'm sure you heard this before, that the light is a bunch of photons. So photon is a quantum particle behind electric field. So electric field is actually the wave function of a photon. And therefore, if you want to find configuration of electric fields with many sources, you simply sum those electric fields, because psi is a vector in the linear space, in a vector space, and therefore it's very, very natural to sum psis. So the superposition principle at the level of electrostatics is exactly the same as superposition principle at the level of quantum mechanics. At the same time, if you want to find probability in quantum mechanics or energy density in electrostatics, and I don't want to explain this, but there is an easy way to see that energy density is essentially the same as probability. They have the same physical meaning because they count the number of photons in the certain unit volume. So energy density is quadratic in electric field, exactly the same way how Born rule tells you to take psi and take square of it. Okay. All right. I want to conclude with quantum mechanics and explain the following, unless you have questions, and then I will not make a pause. But if you have questions, please interrupt myself. I will be ready for that. Quantum mechanics is not a conventional way of thinking about the world, but first of all, it's a physical reality, and second, it's a mathematical framework which is peculiar. In some ways, it's unique, and there are many theorems which show that it is unique. But strictly speaking, we do not fully understand if outside of literally quantum mechanics, this mathematical framework is good or not. And my talk is essentially a discussion of this question, of this mathematical framework is good or not for something else outside of quantum mechanics. But nevertheless, this framework is such that you have complex valued functions psi, and then you can go to probability distribution using this formula. Okay, and this is all we need to know. If you grasp this idea that at quantum mechanical level, you have certain complex valued function psi, and if necessary, you can build probability distribution using this formula, then we are good to go. Then you will be able to understand the rest of my talk. Okay, my next slide is about why quantum mechanics is different. So there are many levels at which quantum mechanics is different. First of all, it's different from classical mechanics at the physical level, as a physical theory. This is something which is important for us physicists, but maybe less important for you if you want to do machine learning and neuroscience. Nevertheless, I want to mention that first of all, the superposition principle is not something outside of electrostatics which we observe in reality. If you have tail up or head up, you cannot have a coin in a superposition of two states. That's simply impossible at classical level. And then another very important thing is that probability or ambiguity is intrinsic to quantum mechanics. You cannot get rid of it. Okay. And then another very important thing is what is called entanglement. And I want to explain what it is. It's a little bit technical, but it's actually something which I hope you will get from my talk and maybe not use immediately, but this will be a concept which you will remember, and at some point it might prove useful. In quantum mechanics, this is one of the very, very central concepts, and if you learn it, it will certainly enrich your horizons. So widen your horizons. So let me spend some time to explain what entanglement is. And just an announcement before I go into details, entanglement is something intrinsically quantum mechanical, and entanglement as a phenomenon is what distinguishes classical world from the quantum world. And to discuss entanglement, we need to imagine a physical system which consists of two parts. And if it consists of two parts, then there are states of one part, and then there are states of another part. And classically, we will try to describe it by the probability distribution. We will say that there is rho of x and y, and that's a probability of a system of subsystem A to be in a state x, and simultaneously of the subsystem B to be in a state y. So that's the language which I'm sure you're familiar with. But quantum mechanically, that's not what we do. Quantum mechanically, we say that there is a wave function which describes the simultaneous state of the full system. So we have a possible state of the subsystem A, that's X, and we have a possible state of the subsystem B, that's Y. And then we have not the probability, but the probability amplitude that your system is in simultaneously in both states. But it's not a probability, that's what I want to stress. Then mathematically, you can do something which is called Schmidt decomposition, and you can represent your wave function as a function, as a vector in the vector space. You can represent it as this sum. And here, lambda are complex numbers, and vectors psi1 and psi2 with the index I form certain orthogonal set, not necessarily basis, but orthogonal set in the Hilbert space, in the space of quantum states of subsystem A and in the Hilbert space of the subsystem B. And then if it so happens that there is more than one lambda, there could be only one lambda, that's fine. If there is only one lambda, then it actually means that your subsystems are not talking with each other. And in this case, it would happen that the probability distribution, which you calculated from the Born rule, would be a product of two probability distributions. And then it simply means that two subsystems are completely ignorant about presence of each other. They live completely independent lives. But unless there's only, unless this is the case, and in case there are more than one lambda, those two subsystems know about presence of each other, and they are correlated. And at quantum level, we say they're entangled. Okay? And as I announced already, entanglement is a completely fundamental concept. Mathematically, it's nothing special. It's actually very, very simple, very, very trivial thing. Mathematically, you say, well, I have two subsystems. So your wave function psi can be understood as a wave function of x and y, where x and y, let's say, would be discrete variables. X belongs to SA and y belongs to SB. So these are two discrete variables, and you can represent the wave function psi of x and y as simply this way. So it becomes a rectangular matrix. X is a discrete index and y is a discrete index. So you have a rectangular matrix. And then it takes maybe just a little bit of thinking, and it's okay. And it's okay if it's not obvious from my slide, because usually this kind of thinking should be done in a quiet environment when you just stare at the formulas. But let me tell the answer. Schmidt decomposition, after just a little bit of thinking, will immediately prove to be singular value decomposition of this matrix. Okay, singular value. So psi is a matrix, and it can be decomposed. Psi of xy is a matrix. It can be decomposed into a product of unitary, diagonal, and another unitary, or you can also say orthogonal, diagonal, another orthogonal if psi is real. And then D will have lambdas on the diagonal, and then rows or columns. It's difficult for me to figure out, but you got the idea. Rows or columns of this one will be vectors psi1, and correspondingly columns of vector or rows of matrix V will be vectors psi2. So mathematically, Schmidt decomposition is nothing special. That's just singular value decomposition. And then it so happens that in your singular value decomposition, if there is more than one non-zero singular value, it means that subsystems are talking to each other, and probability distribution will not be a product of two probability distributions. Now, there are theorems and experiments which can show that if you have two entangled subsystems, you cannot describe them classically, meaning that there is rho of x and y, which you can assign to such a complex physical system. But there are theorems and experiments which show that this probability distribution does not fully characterize the physical system. So it's never the case that you can forget about psi and only work with rho. And that's what I want to emphasize. At the level of quantum mechanics, if you know psi, you can have rho. But there is no way to go from rho to psi. You lose information if you only talk about rho. And therefore, it's very important to always speak about psi. Then what is entanglement? Well, entanglement is a physical phenomenon. It's a phenomenon when two subsystems are correlated in some funny way. But at the colloquial language, people also say entanglement when they actually mean entanglement entropy. And entanglement entropy is a quantitative characteristic of entanglement. And it's a quantity like this, lambda I modulus squared. These are actually probabilities. These are classical probabilities of finding your system in a state when subsystem A in a particular state psi1 and system B in a particular state psi2, and therefore lambda I squared can be interpreted as probabilities, and you can easily see that this formula becomes pi logarithm pi, and depending on your background, you would simply say that this is either Shannon entropy or Boltzmann entropy. The formulas are the same. The interpretation is different. Shannon derived his entropy for one context, and Boltzmann derived his entropy for another context. And but mathematically, these are the same. And this formula in physics, they're slightly different because of pi, you have lambdas. This is called von Neumann entropy. Von Neumann was a mathematician who contributed greatly toward development of quantum mechanics. So this is called von Neumann entropy. And in the context of splitting your system into two parts, this is what is called entanglement entropy. So I told you about von Neumann, Boltzmann, and Shannon just for the background. You can forget about all of this. And whenever you hear that people talk about entanglement or entanglement entropy, they are talking about this quantity which characterizes to what extent two subsystems are talking to each other. If entanglement is 0, then two subsystems are completely uncorrelated, and the joint probability distribution is just the product. But in all other cases, when S is non-zero, those two systems are talking a lot to each other. And of course, the larger entanglement is, the larger S is, more correlations you will find between two subsystems. And there is a way to quantify it, which I will refrain from going into today. Okay. Colloquially, what I want to say without, yes. There is a question, and let me, give me a second. What does I stand for? Well, I assume the question is about this. I is an index which in principle runs from 1 to whatever number of singular values, non-zero singular values you would have. If you have a rectangular matrix psi xy and x runs from 1 to the size of SA, I assume that SA is a discrete set. That's the simplest possibility. And Y runs from 1 to SB, the size of the set B. Then psi is a rectangular matrix SA by SB size, and whatever is smaller, that number is the maximal possible number of singular values. So in principle, I runs from 1 to minimum between SA bar. Bar means total number of elements, like this. So I runs from 1 to the minimal value. But if you're lucky, I could be less than that because all other lambdas would be 0, and there is no point to write in your sum 0, something 0, right? If you have a sum, all 0 terms can be thrown away. Did I answer your question? If I did not, maybe you can follow up with your question in the messenger. In the meanwhile, okay. All right. So without going into formulas, I want to build sort of intuition, or just maybe tell you something to remember, that entanglement qualitatively, or entanglement entropy qualitatively, it's a primary measure which physicists use to characterize how rich or complex quantum state is. The word complexity I put into quotes because there's whole literature about complexity of quantum states, and there's way how people mathematically define it and so on and so forth. So one has to be careful. But at the level of intuitive knowledge or qualitative knowledge, more entanglement your state is, more complex or complicated or rich it has. And if your state is pure classical, uninteresting, which describes uncorrelated parts, then entanglement will be 0 or almost 0. So that's an important intuition. If you remember this part and forget about everything else, I would consider my talk a success. If you remember that later on, and whenever you need to return back to this topic, we will know that entanglement is the first quantity to look at. And again, if you remember this thought, I think my talk is a complete success, and I would be completely happy with this. So in physics, entanglement is a very, very well studied quantity because it's one of the central quantities we study in quantum mechanics. And why that happens? Because there is a curse of dimensionality. If you try to consider a quantum system consisting of n simple parts, and let's say each simple part is a quantum coin, which could be either up or down, or of course a superposition. And the quantum coin is called the quantum spin. The spin could be up or down, or even better term. So quantum spin is a completely correct term, but it actually refers likely to a physical particle like an electron, where you do the experiment and you really have a spin up or down. And in modern language, people try to speak about abstractions, and they speak about qubits. A qubit is a quantum bit. Quantum bit. So that's the term which emerged in the context of quantum computers. And that basically qubit describes a quantum system which has only two states, up or down. And of course, since it's quantum, it could be in any superposition. If you have n such qubits, then there is 2 to the n possible combinations of ups and downs. And according to the laws of quantum mechanics, and therefore there will be n binary variables Si with I. It's a different I. It's not the I from the previous slide. It's a new I with I running from 1 to n. And there will be 2 to the n possibilities of Si, possible total combinations of values of Si. And according to the axioms or laws of quantum mechanics, we know that we need to parameterize this system by the probability amplitude or the wave function. That's the function which lives on the space of these 2 to the n discrete possibilities. So it means that our wave function is a vector in this complex dimensional, in the complex space of dimension 2 to the n. Let me remove highlight, and you will see that psi is a vector in the space c to the power 2 to the n. That's not a typo. So you see that as n increases, the dimension of complex space grows exponentially. It grows exponentially with n. If n is equal to 10, 2 to the n is roughly 1,000. It's 1,024. If n is 20, it's a million. If n is 30, it's a billion. So you see that very, very soon, if you only have 30 quantum coins, if you have 30 qubits, it's not such a big deal. You only have 30 binary variables. You need to be dealing with a billion dimensional complex space. And of course, there is no numerical, no analytic way to deal with such a huge complex space. That's called curse of dimensionality. And it's everywhere from machine learning to numerical, linear algebra, and of course, to fundamental quantum mechanics. This curse of dimensionality, it has two sides, because on the next slide, I will try to explain that it's both a curse and a blessing, because if you actually can control your physical systems, quantum physical systems, there is a way to build a quantum computer. And I want to mention this because it's actually conceptually very much related to what we are speaking about today. But physicists realized there is this curse of dimensionality, and we need to do something about it. But they started thinking, is it true that all of these huge dimensions are important to us? Is that really true that we need all vectors? Of course, we're talking about complex space. So it's even if you have two-dimensional space has two basis vectors, and the total number of vectors is infinite, right? It's parameterized by two variables, but it's infinite. But when we speak about directions, we can simply say that we have direction 1 and direction 2 and think about their combinations. So speaking about 2 dimensions or speaking about 1 billion dimensions, is it true that all of them are necessary for us? And they started thinking hard, because if all of them are necessary for us, we are doomed. There is no way for us to do anything in a billion dimensional space. But very soon, physicists realized that in many, many physical applications, relevant states which we really need to study, are not arbitrary. They are not of general form. There are states which have what is called low entanglement. So more specifically, that emerges in the context of one-dimensional quantum systems, so one-dimensional spin chains, when you arrange your spins in a row or quantum bits in a row, and you only allow neighbors to interact. Where is interaction necessary? The interaction is not present anywhere in the framework I explained so far, but interaction is necessary when it comes to the question which states are important. So I'm skipping that part. I don't want to go into details how interaction defines which states are important. I'm skipping that. But once you go through this and you see which states are important, you see that for genuinely one-dimensional systems, the states which are important, they have low entanglement. You have quantum spins up and down. There is n of them. And then you have a quantum state psi. But when you try to split your physical quantum system into two subparts, A and B, and you try to measure entanglement between A part and B part, and here you have K spins, and here you have N minus K spins, if you try to measure it, it actually turns out that entanglement, or entanglement entropy to be more specific, it will be bounded. You can have N very large, 20, 30, 50, 1,000, doesn't matter how large, how many spins you will put on a line, and you can make a subsystem A to be as large as you want. You can make subsystem B to be as large as you want. K could be huge, N minus K could be huge, but entanglement of physically important states will not grow. And that's truly a breakthrough, because once you understand that curse of dimensionality can be, not overturned, but it can be avoided, because you really don't have to work with all states in this Hilbert space. There is a much smaller subspace, and you will be happy if you can describe that one. So for one-dimensional systems, it works wonders. Unfortunately, for higher dimensional systems, already starting with 2D, this is not necessarily the case. If you want to reliably describe two-dimensional systems, physics of two-dimensional systems, you will actually have to be able to describe states with rather large growing entanglement. And that's a problem which is still not solved. And that's why physics of two and high dimensional spaces, two and high dimensional systems is very, very difficult. Okay. So this is perhaps conceptually the most important slide of my talk. It's about entanglement, quantum computations, and machine learning. We know from the first principles that if you want to have a truly rich, truly capable, if you wish, quantum state, to have a full power of quantum mechanics, you must have highly entangled states, and you cannot avoid curse of dimensionality, and you must work in high dimensional spaces. And that's the promise of quantum computers, which I wanted to mention here, that actually, instead of trying to work with these high dimensional spaces on a classical computer, you may hope to build a quantum hardware which will automatically implement these highly dimensional vector spaces and work with arbitrary, very complex vectors, and it will be able to perform computations, and it's a known theorem, it will be able to perform certain computations which classical computers cannot perform. It will outperform classical computers. And from here comes the promise of quantum machine learning. This is a promise. This is not anything practical at the moment, but if you can build a quantum computer, sure, you can do machine learning way more efficient on that quantum hardware than you can do it on a classical hardware. Okay, so that's a promise. But without a quantum hardware, and we do not know if we ever will be able to build such a quantum hardware, the curse of dimensionality bites you big time, and you need to do something about entanglement. And the question is really entanglement important? It's important for physics in higher than one dimensions, sure, but is it important somewhere else? So that's the big question which people are discussing now and have been discussing for the last, I do not know how many years. And that's the question which I also want to emphasize, because it even have certain consequences for neuroscience, if you wish. For example, one can ask a question if a human brain is a quantum computer. It's, of course, a very speculative question. And usually people who discuss such questions, they usually make statements which are not scientific. But if you're curious about this question, I can recommend talks by Matthew Fisher, who is a condensed matter physicist from University of California, Santa Barbara. He's certainly a very knowledgeable person, and he is trying to discuss, is it possible that human brain as a physical system is capable of doing quantum computations? Is it physically possible that our brain operates quantum mechanically, in a sense that entanglement is important? It's likely not, but if you're curious, I recommend you Google his talks and watch them. But also more recently, outside of neuroscience and in a more sort of developed framework, people started discussing, is large entanglement important outside of physics for other applications, for example, of machine learning? At classical level, entanglement is purely, it's intrinsically quantum, but at classical level, entanglement can be traded for what is called mutual information. That's how much one subpart of the system knows about another subpart of the system. And people very, very recently, this year, in March of this year, we're discussing how much mutual information we really need to be able to process to do effective machine learning with real world data, like images and speech and so on and so forth. So this idea is coming from the following important idea, which is main idea of my talk, which is main idea behind my talk. The idea is the following. If you're a physicist and you're familiar with quantum mechanics and entanglement, and the fact that in one dimensions, physically relevant states have low entanglement, and the fact that low entanglement simplifies things a lot, you can ask the question, maybe for real world applications, for machine learning applications, large entanglement is not necessary. And if you say that it is not necessary, you will immediately result with an idea that tensor networks should be used for machine learning. At this point, this conclusion is unclear because they never explain what tensor networks are and how they emerge from quantum mechanics. I will explain that in the rest of my talk. I still have 30 minutes to do it, but I want to emphasize how a physicist looks at this situation with tensor networks and machine learning. For me as a physicist, as well as for many other physicists, the story is very, very clear. We knew that entanglement is a very, very important measure in quantum mechanics. And we knew that there are important physical situations, not universal, but there are important physical situations when low entanglement is sufficient. And then you immediately can ask a question, is it true that low entanglement would suffice for machine learning applications such that image recognitions or sampling or speech processing and so on and so forth? And once you start thinking in this direction, you will basically end up with tensor networks applied for machine learning. Okay, so this is an important milestone in my talk because basically it explains, at least for part of the community, how the story looks like. Of course, there is other part of the community which has no background in physics, and for them, tensor networks is just computational tool, and they cannot care less about all this quantum physics and quantum stories. But I specifically wanted to tell you about those concepts because I believe they're important. And even if you understand them qualitatively at the level of concepts, at some point they might prove useful. Any questions or comments at this point? Let me switch the view such that I can see the room. I don't see any, Sasha?
No questions yet.
Okay, wonderful. Okay, let me try to proceed. And I have only 30 minutes, and I actually want to tell you some technicalities. So what is the tensor network? From where it comes? Technically, it comes from the following idea. Physicists wanted for the last 50 years, or at least 40 years, they wanted to describe states with low entanglement. And they started with the Schmidt decomposition, which is the same as singular value decomposition. You have a matrix with two indices, and matrix with two indices can be decomposed as a product of three matrices: unitary, diagonal, and another unitary matrix. And you can schematically represent it as this. A matrix can be represented as node with two indices. This is S1 and S2. And you can write it as something like this is S1 and then I, then you have another matrix. I will be this bond between them, and this matrix lambda, and then it will be another one, and this is S2, and this is psi1, and this is psi2. This is just a visual representation. This visual representation could be stupid because you say, well, these are just matrices, this is a diagonal one, I understand everything, but actually visual representation is very, very helpful, because once we try to go from Schmidt decomposition of a state which describes, in this case, the state describes two qubits. S1 is equal to 0 and 1, and S2 is, oops, I'm sorry about this. Let me decline this. Just 1 second, I'll try to go back to, yes. Okay, so instead of having two qubits, we can actually have two qubits such that S1 will have values from 0 to D1, and S2 will have values from 0 to D2, and mathematics will be exactly the same. Nothing will change here, and nothing will change with this symbolic equality. And also, if you now have n qubits or n qubits, you can split them into two groups, k spins or k qubits and n minus k ones. And then you can write this in the following symbolic form. You can say that you have a state with n legs, and you can represent it as a bulb with k legs, and then you will have something here, lambda. So this is your psi1, and you will have psi2, and then you will have another n minus k legs. Okay, this is still singular value decomposition where you split your system into two subsystems, A and B. Okay, but then, and there is no loss of information. Mathematically, this is just exactly, this mathematical is just rigorous thing. What we did here very quickly, and since we did it very quickly, maybe it was not very clear, but very quickly, we introduced visual ways to write down psi. So we just, instead of writing formulas, we succumbed to writing pictures or drawing pictures. And then we wrote this formula in this way. That's what we did. Okay, this is a visual way, but if you have a lot of indexes, if you have only 2 or 3 indices, this visual way is not helpful. It's maybe even confusing, and you would prefer to write matrices explicitly. But if you actually have a lot of indices, apparently drawing pictures is way more productive. So the idea behind matrix product space is the following. At the level of splitting the system into 2, you're not losing any information, but that's not good enough, because you might have a need to lose some information and be able to only to describe low entanglement states to overcome the curse of dimensionality. And the idea is the following. You say you have a state with n legs, but you will represent it in the following form. You will say that it will be a product of tensors. Each tensor will not have more than 3 legs. First tensor will only have 2 legs. Second tensor will have 3 legs. Another one will have 3 legs, and so on and so forth until the last one, which also will have 2 legs. So schematically, this is written here, and this could be understood as an ansatz, the form in which I write my state psi. You can make it mathematically completely rigorous. That's fine. You can make it rigorous. But the price you will pay is that the internal index I, so here it will be I1, here it will be I2, index I in principle will have to go through a lot of values. More specifically, if your original indices S1, Sn are binary indices, so each S can only take 2 values, 0 and 1, and index Ik, which splits the system into k and n minus k, would have to, in principle, take values from 1 to 2 to the power k, or 2 to the power n minus k, whatever is smaller. But if n is large and k is large, both of these values are exponentially small. So in principle, internal indices would have to be able to take exponential large values, and your curse of dimensionality is not gone. It's still there, and you gained nothing. So the idea was to say, okay, at this point, we are abandoning hope to describe all states in my Hilbert space, specifically the states with large entanglement. We are only focusing on states with small entanglement, and therefore we say that all internal indices I whatever, IL, they will be running between 1 and D. And D is called the bond dimension. And this D, actually it's written here, and this bond dimension controls maximal entanglement. You bound your entanglement from above with this ansatz. So now this formula can be understood as an ansatz. Matrix product state is an ansatz. Maybe that's not how people refer to it, but at the simple technical level, it's an ansatz. And if the bond dimension is bounded, it means that your entanglement is bounded roughly by logarithm. I think it's D logarithm 2. The coefficient doesn't matter, but the idea, the exact formula doesn't matter. What matters is that if D is finite, your entanglement is finite. So you have a very powerful tool to write down states with low entanglement, but you will certainly not be able to write states with large entanglement. So far, D is small. And you need to keep D small because otherwise you will not be able to do anything practical with this representation. So in a nutshell, what I explained here is called matrix product states. This representation was developed, I'm not sure, 40 or 50 years ago by physicists. And then more recently, about 10 years ago, mathematical equivalent representation started appearing in numerical linear algebra literature, namely my colleague from Caltech, Ivan Vasilidets, introduced the term tensor train, but my understanding is that tensor train is literally the same as matrix product state. And he not only introduced this term, he actually developed he further developed mathematical theory, how to find these representations and how to work with them. So this idea of representing states with small entanglement, although that was not a motivation for Ivan because he's not a physicist, but he basically reproduced this idea from the point of view of numerical linear algebra. He was guided by the hope or desire to build more efficient computational algorithms. And then he basically came to this idea that entanglement should be small, although the term entanglement was not present in his works to the extent I understand. Okay, so what do we do with these matrix product states? Well, there are some technicalities, like with singular valued decomposition, we represent the tensor as a set of unitary matrix and then diagonal, and then maybe another unitary, and then we can combine those two into something else, which is not unitary, but this is still unitary. And since this is unitary, if we combine those two unitaries together, this will be an identity. The same trick can be used with matrix product state representation in general. And when you have, well, a tensor train, let's call it a tensor train or matrix product state, and then you can try to contract it with itself, then you can bring it to the canonical form such that this part, let me highlight it with another color, this part will be equal to simply identity. You cannot make this identity up to the end. There should be some place, it could be almost up to the end, but it should be some place where you have to stop, and at least one node will remain uncontracted. But there is a canonical form such that to the left of this line, everything can be contracted to one, and to the right of this line, which is, this line is called orthogonality center, everything can be contracted to one as well. And why this is important? This is important because contraction of matrix product states with itself is a very, very efficient computational thing, computationally efficient thing. If you have a subsystem, if you have a state of certain number of spins and you split it into two parts, A and B, and you want to calculate a state only of the subsystem B, or vice versa, only of subsystem A, then you need to contract all indices of the subsystem A with itself, while these indices remain hanging. And as a result, you will have density matrix. This is the formula written here. This is computationally something very, very efficient. And that was the reason why people introduced MPS in physics. And that's why Ivan introduced them as well, because you can do calculations with high speed. Another technical development about 30 years ago, physicists, namely Steve White, developed an algorithm, which is an algorithm to minimize certain functionals involving psi. Well, he was interested in minimizing energy, but I will not go into details. That's a very computationally efficient algorithm to minimize certain functionals, which include psi. It's not exactly the gradient descent. It's different, but in certain contexts, it's the best one. Why this is important? Because very soon we'll be using all of that for machine learning. So I have 4 slides left and 20 minutes. Let me pause and try to summarize what we have learned so far. First, we learned that probability distributions naturally emerge in quantum mechanics. Quantum mechanics, as an area of physics, it's all about probability distributions. But they're not necessarily parameterized by probability raw. There is more fundamental way to parameterize them with help of the wave function psi, and rho can be calculated from the wave function, not the other way around, but rho can be calculated from the wave function. This is an initial thought. Second thought, complexity or difficulty or richness of psi is parameterized by entanglement. If entanglement is 0, your state is essentially classical, so there is no reason to talk about quantum mechanics at all. But when you have large entanglement, then you have truly quantum states. Okay, so this is also something we learned today. And finally, in certain contexts, people saw that, of course, 0 entanglement is not interesting. This is trivial. There is no point to study it. But in certain contexts, people saw that relatively small entanglement, people saw that relatively small entanglement, finite entanglement, which doesn't scale with the full size of the system or the total number of variables involved, is already interesting enough and physically relevant. And you can find what is called ground states or one-dimensional quantum systems or something like that. Doesn't matter what exactly. It matters that moderate entanglement is already very, very interesting and can answer important questions. And physicists started working very, very hard, and then they developed computational techniques, which is called matrix product state, and later which were rediscovered under the name of tensor trains. And they describe low entanglement states, and they also devised efficient optimization algorithms. One of the most efficient one, the most famous one, is called DMRG, density matrix renormalization group. That's the story. There is no machine learning here yet. Yes. The question I have is the following: how do we know the entanglement is small? In the case of physical context, in the context of one-dimensional quantum systems, even without calculating psi, there are physical theorems, rigorous theorems, which tell you that entanglement of psi will be small. Now, it's a miracle because you do not know psi, but sometimes in physics, fundamental physics or mathematics, even if you do not have the object at your hands, you didn't find that object, you can study properties of that object. That's exactly one of those instances. You don't have psi, but we know that the correct psi has a relatively small entanglement, and that's a rigorous result. Okay, so once we have all of this picture, the next step is very conceptually clear. We say, let's use all of this for machine learning. We do not know if low entanglement will suffice for machine learning, but let's try. Let's at least try, because we know that in certain physical concepts, that was such a great idea. And this idea I will highlight it, I will emphasize it. Some people might look at tensor networks for machine learning from a completely different point of view, and that's fine, because that's not the question which can have only one answer. But this point of view is certainly valid, and there is certainly a community of people who think about tensor networks through these glasses, if you wish. And I wanted to share with you this particular vision. So the idea is, okay, let's try low entanglement. Let's see how well it will work. I do not know when the story really started. I was trying to write down some pioneering papers. I'm not sure if these are the very first ones, but it looks like the story started picking up 5 years ago in 2016. Although it might be that some people tried something else before, so I cannot be completely sure. I think this paper is more theoretical, and it simply said that, you know what, it's a good idea to try to use tensor trains or MPS representations because of this and that reasons. So it's more theoretical. But already in May of 2016, Ivan with his collaborators and also a group from the US, Miles Studemeyer and David Schwab, they use matrix product states or tensor trains. Two groups called, of course, the representations differently, but the idea is very, very similar. And the time of publication was similar. They use it to do, to perform simple tasks of machine learning. I'm more familiar with this work. Although two works conceptually are similar, and I will be mostly speaking about this work. And the idea is the following: we take tensor train representation, MPS representation, and we try to use it to approximate probability distribution, which doesn't come from quantum mechanics, but which comes from real world data. In the case of this paper, it was the MNIST images, but you can think about any other images or language or videos or whatever real world or neuroscience data, whatever data you want, and whatever machine learning task you have, you need to approximate rho of X. Try to approximate it using Born rule by finding appropriate psi, and that psi try to represent in terms of MPS or tensor networks. That's another name for it, and that is basically the idea. And from the very beginning, it was clear that pretty much this works. It works. You can use low entanglement states to do simple tasks of machine learning. In case of Studemeyer and Schwab, they used MNIST images, and I want to give you just a few details of their work. So MNIST images are n squared by n squared, n by n images, and I think is equal to 28. Each pixel is black and white, so you have image being represented as a vector in this Euclidean space. And then each pixel is a real variable between 0 and 1. 0, let's say, would be white and 1 would be black, or other way around. And then each pixel will be mapped to a state of an auxiliary imaginary quantum spin or quantum qubit according to this formula. Studemeyer and Schwab used nonlinear map. They used the sine and cosine to make the map nonlinear. And for a while it was thought, so if you're used to think about conventional neural networks, you think that the first layer had certain nonlinearity in it, and everything else would be completely linear. And for a while, people were thinking that this nonlinearity is important, but more recent understanding is that that might not be important because people already learned to do supervised learning tasks with good accuracy without nonlinearities in the input layer. But nevertheless, for simplicity, we will follow what they did. They have nonlinearities here, and then if you have the full image X, you have the full image X. Full image X is a collection of pixels. Then each image would be mapped to a quantum state according to this formula. And if you're familiar with these notations, it simply means that each pixel lives its own life. Each pixel as a quantum state, they're not entangled between each other. So the state which you associate to each image is a completely classical state. There is no quantum mechanics involved. But that's the input data. The state of your network, psi, will be described by an MPS, and it will be not highly entangled, but it will be certainly an entangled state, because your task is to find an MPS state, not actually one, but 10 of them, because you want to classify MNIST. You want to have 10 tensor networks psi A, and then you use Born rule to calculate probability, and then you try to minimize the loss function. This is a completely standard loss function which you use. So this is a probability according to the Born rule. And this is a completely standard loss function. This is not the one which was used by Studemeyer and Schwab. but this is the one which was used in later papers. So I sort of combined their input layer with more later works for conceptual simplicity. I think the loss function they used it's abandoned right now. People, I don't think they use it anymore. So in a nutshell, that's if you try to solve the simplest supervised learning task, that's what you do. You write psi. Let me try to reiterate it once again. You write psi using MPS, and then your loss function is the conventional one. It's a logarithm of a probability, and you calculate probability from the Born rule. That's what you borrow from quantum mechanics, and then you use DRMG. That's what Stoudemire and Schwab used to minimize the loss function. Or more general technique, you can use gradient descent to minimize the loss function, and you find psi, and that's it. That's the result of your supervised learning, and it works. Maybe it works on par with deep learning algorithms. Maybe it's not beating the most efficient one, but it's certainly in the same league as the modern deep learning algorithms, neural network algorithms. Okay. So let's speak about further developments. During the last 5 years, this idea of using tensor networks started picking up, and people realized that many other things can be done. First of all, it turns out that DMRG, which was developed for physics, it's not so good for machine learning applications, because DMRG is good when your loss function is a polynomial in psi, especially when it is quadratic in psi. But in machine learning, we like the loss function to be a logarithm of something. And in this case, you have nonlinearities, and then DMRG might not work as well. Stoudemire and Schwab were trying to fix that. But more recently, people started using gradient descent, and it looks like it's working better. And then another very important thing that besides supervised learning, you can also do generative models. And you can do generative models because you can use psi of x to learn particular rho of x through the Born formula. But that's not good enough. If you want to sample something, the fact that you learn probability distribution and we're able to represent your rho this way is not good enough. You should be able to efficiently sample your images. Let's say that you're talking about images. And apparently tensor networks are very, very naturally predisposed for this. This is because, I was trying to explain, this is because you have this canonical form. And if you have a matrix product representation with a lot of legs, and then you need to construct all legs, let's say, but one, you can do it very, very efficiently. And what you obtain as a result of this, you have a density matrix or density probability distribution just for one spin. So this is a probability distribution just for one spin or one qubit or one pixel. So this can be done in no time. This mathematical stuff, this mathematical task can be done in no time on computers. It's a highly efficient numerical algorithm. And once you have the density matrix just for one pixel, it basically means that you have one classical pixel which you can sample with a probability distribution provided by this rho. So this rho has, this rho has two values. Rho 0, 0, this is a probability of this pixel being, let's say, black, and the rho 1, 1, that's a probability of this pixel being black, or white and black. Or you can also have grayscale, that's fine. So with one pixel, you can sample it, it's a Bernoulli distribution, you can sample it easily. What you do at the next step, you reconstruct such that you have everything contracted by 2, but this pixel has been sampled already, so the value of this leg is known and everything else was contracted. And from here you have as rho S2, 2, conditional S1, 1. So that is already known, so forget about it. Again, you have a probability distribution for the second pixel. Now, I understand very clearly that the way I explain it here, it's difficult to understand because I just introduced these cartoons a couple of minutes ago. And if that's the first time you see them, it's very unlikely that you really follow in detail what I'm trying to do here. But the idea which I want to convey is the following. The mathematical apparatus of MPS allows you to effectively calculate probabilities for each pixel which you try to sample iteratively. So you sample pixels one by one. You sample one pixel with a probability distribution just for one pixel. Use this information to effectively calculate the probability distribution for another pixel. Then you have a large image and you sample pixels one by one, but you do it computationally very, very efficiently because MPS or tensor trains are designed, they're hardwired for computations which allow you computation of a probability distribution of a particular pixel. And this idea was recognized a few years ago, and there are two papers, which I think pioneering papers, essentially by the same group from China, which started using MPS representations for generative models. And now this is also a growing subfield. There are, of course, many other developments. For example, Ivan, with his group, his collaborators, use tensor trains to learn abstract probability distributions. And then also there are examples which we know from physics or otherwise when small entanglement is not good. For example, there were interesting papers by Vasily Pestin and his collaborators 4 years ago. They started looking into speech recognition or maybe language processing more generally. And they saw that small entanglement is not good enough. They saw that actually to effectively solve those problems, you need growing entanglement. At the level of concept, that's very similar to what happens in physics. In physics, we know that when you have two-dimensional physical system, entanglement must grow. And therefore, MPS or tensor trains, they're not good enough. They're not good enough because their entanglement is basically limited by the size of the bond. But what you can try to do, you can try to do something like a hierarchical network, something like a pyramid structure. And then it turns out that if you have something like a pyramid structure, it has many different names. There is a particular one, if you want to take a note, it's called MERA. That's a particular design of a tensor network, which actually has growing entanglement. It's more computationally difficult than MPS, but at least it can accommodate growing entanglement. And the ideas of using more complicated tensor networks, both in physics and in tasks such that language processing is also getting traction now. And I have only a few minutes, so let me try to start concluding. More recently, people at Google, there is a group which they developed the whole library. It's called the Tensor Network. That's the library which is operating, it's operating at the engine of TensorFlow. And this is the library specifically designed for building different machine learning applications using TensorFlow network. And since TensorFlow is optimized to work very efficiently on hardware and GPUs and so on, now you can do different computations with tensors also very, very efficiently. So now with Google joining the game, this is certainly tensor networks is certainly a part of the, well, maybe not the most popular tool, but it's certainly part of the mainstream. And it's becoming one of the standard elements of the standard toolkit of a machine learning practitioner. And here's my conclusion. Tensor networks in general, not only MPS and not only tensor trains, but in general, tensor networks, they emerge in physics as a robust computational approach to describe low entanglement states. And in physics, there's huge history for that. And in computational numerical linear algebra, there is apparently history for that as well. About 5 years ago, maybe a little bit earlier, people started applying tensor network techniques towards standard tasks of machine learning, such as classification, and more recently to sampling and so on and so forth. And almost immediately, they started getting encouraging results. Those algorithms, they are in the same league as contemporary neural network deep learning algorithms, although they're usually not beating them. If you have the most sophisticated neural network algorithm, usually the tensor network algorithm is somewhat behind it, but it's in the same league. Now with Google joining the game and Tensor Network being implemented as a library as a part of the TensorFlow, Tensor networks are certainly gaining acceptance by a wider community of machine learners, and it becomes one of the standard methods in the machine learning toolkit. That's all good. That's wonderful. But I think there is a very important question remaining open. And this question may be the reason why I was invited to give this talk today. And certainly this is the question which partially guides my research and my interest in tensor networks. I didn't speak about my research on the subject, but and it's not important, but I'm certainly guided by this question. The question is the following. We understand that tensor networks work well when there is low entanglement, but we do not really know when in life, which data, real world data, has low entanglement. And therefore, we do not really know conceptually what are the right places to use tensor network-based methods. And if, for example, we can use them efficiently for neuroscience and areas like that. So that is the question I would like you to think about. And thank you very much for your attention, and I'm done.